Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our fifth set of notes, where we finally get into quantum theory of the atom, and we're finally looking at the electron rather than just at light. Now, the scientist who really advanced our understanding of the electrons a significant amount was a scientist by the name of Niels Bohr. And what he said was the electrons move around the nucleus in circular orbits. Now, as it turns out, this idea is incorrect. But most of the rest of what he said is going to keep sounding familiar because many of these ideas are used as we further refine our model. So ignore the fact that that idea was incorrect, and let's look at what he did talk about that was relevant. Now, what he said was atoms consist of electrons that exist at very specific energy amounts. Remember quantized energy from a previous idea in notes? So he said electrons exist at what he called energy levels inside the atom. The electrons orbit in circles around the nucleus at fixed energy amounts and are quantized. Now remember, the idea that they are moving in circular orbits, eventually we're going to drop away, but it still introduces a term we're going to use a lot in the upcoming sets of notes, which is the term of energy level. Now he said that atoms are stable when their electrons are at their lowest, and he called that the ground state. So it's when the atom's electrons are at their lowest energy levels. And the higher the energy level was, the farther it was away from the nucleus. Now that's still something we will believe and use today. So when the electron is on the first energy level versus when it's on the fourth energy level, on the first energy level, on average, it's going to be significantly closer to the nucleus than when you're on the fourth energy level, and so forth. So that's a concept we still use today. Now, a quantum then is a specific amount of energy, and the reason why light comes out at very specific energy amounts is that the electron can only exist at these energy levels, very similar to what you just watched in a previous short movie. So when the electron jumps from n equals 1 to n equals 2, it's absorbing a certain amount of energy, and it's not stable there, so it's going to fall back down and then release that same specific frequency or energy of light. And the drop from 2 to 1 is different from the drop to 3 to 2, so you're going to get different colors at different drops. And remember our Roy G. Biv, the bigger the frequency, the bigger the energy. So red light is lower in energy, so it would represent a smaller drop than something like purple light would. And it also implies that if the drop was too big or too small, it's not going to be in the visible spectrum. It's going to be above or below visible light. And that's very, very true. Now, building on Planck's and Einstein's concept of quantized energy, which remember means that they can only be allowed at certain values, Bohr proposed that the hydrogen atom only had certain allowable energy levels or energy states. Now, impressively, Bohr's model also correctly predicted the frequencies of the lines that were above and below visible light that we couldn't see with the naked eye. But he could mathematically predict in the infrared and the ultraviolet parts of the spectrum the different frequencies and energies of light that would exist at those. So his model worked beautiful for hydrogen. It not only predicted what we could see in the visible spectrum through mathematics, it could predict what we couldn't even see with the naked eye. So it predicted the visible spectrum as well as those in the infrared and the ultraviolet parts of the spectrum. Now, one of the things that this model relies on is the fact that, remember, electrons are most stable when they're, or atoms, I should say, are most stable when their electrons are in their ground state. And when they absorb energy, they jump up to what we call the excited state. So jumping up to the excited state involves an absorption of energy. And it's not stable there, so it's going to fall back down. And when it falls, it's going to release light. So it absorbs when it jumps and releases when it falls back down towards the ground state. Now, although a hydrogen atom contains only one single electron, then, because it has different energy levels, it could release different frequencies and energies of light, which is something that scientists couldn't explain. Why was one electron giving us multiple colors? His model correctly predicted that. And while it worked beautiful for hydrogen, it completely fell apart and got worse and worse and worse for every atom on the periodic table beyond hydrogen. So it worked great for hydrogen. And then as we got to helium, lithium, beryllium, and others, the mathematics started to fall apart, which meant there had to be problems in the theory. But at its core, it worked beautiful for hydrogen. So maybe the situation was just a little bit more complex than Bohr realized. And it did do something very, very important. It moved us in the right direction. Now, the next person to come along that added to our idea of the electron in the atom and furthered quantum theory was a French physicist by the name of Louis de Broglie. Now, de Broglie proposed an idea that eventually accounted for the fixed energy amount. So why was it that the energy amounts were fixed inside the model? Well, what de Broglie said is if waves could be treated as particles, that's what we did with light, maybe particles could be treated like waves. So what he tried to look at was what about wave properties would lead to the fact that electrons could only exist at certain energy amounts. So Broglie knew that if an electron has wave-like motion and it's restricted to a circle orbit of fixed radius, then the electron can only exist at certain possible wavelengths, frequencies, and energy. In other words, it would be quantized, just like we observed. Now, as it turns out, it didn't move in circular orbits, but he was opening the doorway for scientists to think maybe electrons, which are a particle, could be treated like a wave. Now, as a part of his work, he came up with the wave equation here, which is not something we're going to end up doing calculations with. I just want you to understand the implications of this. So notice it's got h, which is Planck's constant again. It has v, which in this case, it's not the crooked v. This is not nu. This is not wavelength. I'm sorry, frequency. This is velocity. And m would be the mass. So what he said was, if I have any massive object moving at a certain velocity, I can calculate its wavelength. Now, does it actually work? Well, in limited ways, because experiments have shown us that the smaller the particle, the more important its wave properties are. The larger the particle, the less important. So an everyday object like bowling balls and hard balls and those type of things, no, the wave-like properties of that substance really aren't important. But when we deal with something as small as an electron, which is the smallest type of particle we've talked about, now its wave-like properties become very, very, very important. So we were a step closer to understanding what we were trying to find out about the electron, its position and its energy in a predictable way with all of the elements on the periodic table. So step by step, scientists like Rutherford and Bohr and de Broglie were slowly unraveling the mysteries of the atom. But along came Heisenberg. And Werner Heisenberg came to a conclusion that basically disrupted science for a number of years. And rather than try and understand what his principles said, and come up with a way to get around it, scientists wasted a lot of energy trying to disprove what he said. Scientists were trying to find the position precisely and the energy precisely of a particle. And what Heisenberg said was, you're trying to find something that we cannot know. And this is known as Heisenberg's uncertainty principle. You can't precisely both know the position and the momentum. Now, momentum is directly proportional to velocity and energy, so we talk about it from an energy point of view of a particle at the same time. So what he fundamentally said is you're looking for two things you can't precisely know. And then scientists wasted a whole bunch of time trying to prove him wrong. Well, he wasn't wrong. When we're dealing with these smaller particles like an electron, the Heisenberg uncertainty says these small particles, the more precisely we know its energy, the less precisely we know its position. Because finding the position, we hit it with a photon of light, which means in locating it, we've changed its energy. Well, we've now increased the uncertainty of what the energy is. And on the flip side, when we measure its energy, then we freeze it in place and we don't know what its position is. In other words, we have uncertainty of position. So Heisenberg's uncertainty principle really applies in a huge, huge way to small particles like the electron. So electrons are so small that the changes in velocity of the electron that are caused by this lead to uncertainty in momentum, velocity, and energy. So we had a problem. And it was up to other scientists to try and get around that problem. And that man was Schrodinger. And that's where we're going to pick up quantum theory next.